worksheet that says the rotational motion practice problem notes. And a lot of these are just simply conversion problems. Like if you look at the first one, it says a merry-go-round has a radius of 3.5 meters. How far did the person go who spun around 180 degrees move in radians? Well, once again, it's just a conversion problem. So I'm going to take 180 degrees. I want to get those degrees to cancel out and go to radians. So I'm going to put the degrees on the bottom since they're on the top here. And I'm going to put my radians on top. Well, there are 2 pi r is the formula for a circle. So there are 2 pi radians in a circle. There are 360 degrees in a circle. If you want to put that in lowest terms, you could say pi over 180. I think that's what y'all do in math class. And when you go ahead and multiply all that out, you get 3.14 radians. Okay? Well, if you look at the next one, it's a part B problem. So part B problems can use the information in part A. But I want to give you some formulas here that make things a lot easier. If you remember, if you want linear distance was a regular d, but angular distance was theta. So we measure how far we go in an angle using the Greek letter theta. If we want to know regular velocity or linear velocity, it's a regular v, but angular velocity was omega. But for some reason. And if we want to know angular acceleration, it was regular a, but angular acceleration was alpha. We also called it Jesus fish. Okay. Well, what's really cool is this. If you want to know the linear quantity, like the English D, the English V, the English A, all you got to do is take the Greek letter and make it Greek-er. In other words, you multiply it by r. So I'm going to take the Greek letter alpha and multiply by r. I made it Greek-er, and that gave me the angular distance times r gave me linear distance. If you want to find the linear velocity, take the Greek or the angular velocity, which is omega here, and multiply it by r. You just make it Greek-er. And then you take the alpha, that's the Greek acceleration, and you multiply it by r, and that makes it Greek-er. Or you simply multiply the alpha by r, and that gives you English acceleration. So whenever you want to know the linear is the English, you multiply the Greek letter by r, and you make it Greek-er. And so that always equals out there. So let's look at part 1b. It says how far in did the ride move in meters? Well, that's linear distance. So I'm going to put in d equals omega r. I'm sorry, not omega, but theta r. Well, you got to remember this 3.14 right here. That is your theta. That's how far you went in radians. So I'm going to put 3.14 radians. And you multiply that by the radius, which is, I would say 3.5 meters. But that's 3.5 meters per radian, because that's how big a radius was. So the radians now cancel out, and you're left with your answer of 10.99 meters. Now let's go to part C. Part C, once again, we can use everything from part 1A and B. Part C says, what's the angular velocity of the ride if it rotates 0.25 revolutions per second? Well, angular velocity is omega. And in order to find omega, it just simply says 0.25 revolutions per second. So let's just use the conversion factor for this. 0.525 revolutions per second. Well, omega is measured in radians per second. So we got to convert revolutions. Get rid of the revolutions, put those on the bottom, and put radians on the top, because I want to make it radians per second instead of revolutions per second. Well, in one revolution, a revolution is the same thing as a circle. There are 2 pi r is the formula for a circle, so there's 2 pi radians in every circle. And when you multiply the 0.25 times the 2 pi, you end up getting 1.57, or half a pi, radians per second. Now the next one's a part D problem, so I can use all the information from A, B, and C. So it now says, what's the linear velocity? Well, linear velocity is this English V here. So that's regular old V. Well, if you want to find regular v, you can take the Greek letter for velocity, or omega, and multiply it by r. So I'm simply going to take my answer of 1.57 radians per second, multiply that by the radius, which in this case was 3.5. I got that from part B. So 3.5 meters in 1 radian. And when you multiply that out now, you end up getting 5.5 meters per second. This is really easy. You just plug in the numbers like we did before. And what's really nice is that all the formulas have stayed the same. This is now they're written in Greek. So we're going to do part E now. Now it says that the ride started from rest, that means velocity is 0, and reaches a maximum speed of 3.75 radians per second. So that's your final speed in 6 seconds. This is your time. This is your final velocity. That's your time. What's the angular acceleration? Well, angular acceleration is simply velocity divided by time. Now let me show you what I mean by that. If I want to know regular acceleration, right over here, isn't regular acceleration the change in velocity over change in time? Well, when you're going in a circle, it doesn't change. It just becomes the Greek letters. So instead of an A, I'm going to put down an alpha. And remember, regular V was now omega, and T never changed. It's regular time. So I'm going to use this alpha equals omega over T. I'm going to use that for this equation here. So alpha equals change in omega over change in time. And so my final velocity was 3.75 radians per second. Radians per second. My amount of seconds was 6 seconds. And so therefore you divide those two things, you end up getting 0.625. But instead of radians per second, because that's velocity, this is acceleration. So it's always radians per second squared. It used to be meters per second squared, but now it's radians per second squared. Letter F says, well, what's the linear acceleration if it reaches 3.75 radians per second in 6 seconds? So it's the same problem as letter E, it's just now the linear. Well, if you want to know the regular acceleration, instead of using an alpha, we're going to use an A. But the easy way to do it is simply take the Greek letter. So you're going to take the Greek letter for A, which is alpha, and make it Greek-er, and multiply it by R. So I'm going to take my answer from part E, 0.625 radians per second, multiply that by 3.5 meters per radian. By the way, this is radians per second squared. Well, the radians cancel out, and you're now left with, hold on here, that's 0.625, right? So you're left with 2.18 meters per second squared. It's meters per second squared because now it's linear acceleration. Now it asks, what is the frequency of the ride if it rotates 3.55 times in 4 seconds? Well, the frequency is just simply how many revolutions did you go per second. So I'm just going to take frequency here, which is revolutions per second or times per second, because circles per second, however you want to say that. Well, if I went 3.55 revolutions in 4 seconds, you just divide those two numbers. Revolutions in 4 seconds. That ends up giving you 0.88 revolutions per second. Now it asks for the period. Well, the period is the inverse of the frequency. So there's two different ways you can do this. Watch this. I'm going to take period. They usually use a big old capital T. They don't use a P. P means power. So if it's the inverse or the flip-flop of frequency, I can simply take 1 divided by the answer that I got for frequency. So let me write down the formula first. Period is the same thing as 1 over frequency. So I can take 1 divided by 0.88, and that gives me 1.13, but instead of revolutions per second, it's going to be seconds per revolution. Now, if you remember, I said simply the flip-flop of this, so the inverse of this. So I could take this part right here, this 3.55 divided by 4, and simply turn it upside down, I'll get the same answer. Because 4 divided by 3.55 gives me the same answer of 1.13. And 4 was seconds, 3.55 was revolutions, so our period is now 1.13 seconds per revolution. Okay? So once again, I think these problems are really, really easy. Just gotta make a Greek error if you want to find the linear acceleration. And as far as the angular acceleration, use the same formulas we used to. We're just now using Greek letters. Hope you have a great day. Thanks for hanging in there. Bye.